All right. So let's pick up here where we left off. So we were talking about some ways to get at call path information and why that's useful. So just to kind of recap, you'll find this useful when you're trying to figure out what call is to a particular function is actually contributing to the bottleneck or communication bottleneck or whatever it is that is slowing down the code. You want to know which invocation is causing the problem, and so this can help you find that. And it'll link up to your source code and show you where in the source code that call is being made from. So I think we'll see some of that here in a bit. And that is enabled just by setting these environment variables at runtime. So there's a bunch of graphical interfaces that we can look at that'll show this call graph and call path in a number of different ways. So we'll look at those, I think, a little bit later. So we'll talk a little bit about how to isolate regions of code that you're interested in profiling and separating out from the rest. Maybe certain functions, again, are called within different phases, and you don't want them lumped all together, but you want to isolate some region of interest. So you can define a phase, and the way that you do that is through that selective instrumentation file. So remember, at compile time, when you build your application with tau, there's a number of options that you give tau through the tau options variable here. And one of those is you can specify a selective instrumentation file, and that can specify routines that you want to exclude from instrumentation or include. There's various combinations of commands that you can put in there. But you can also specify a phase. And the way that you would do that is by putting something like this in that selective instrumentation file. So you would have static phase, and then here is actually the name. And then here you specify the name. So the name of this phase would be this, and then you just tell it which file to look in and the lines in that file that you want to define that phase. So anything that happens between those lines, it's a small phase, but anything that happens between those lines would be in that phase. Now, this would include any function calls and all the child calls from in that area. So it goes all the way down the chain. It's not. Anything that is called or has a parent that calls it from within these this space here that's defined here will be included in that phase. So this is why. So obviously it's looking at the call path there, and so this is why that getting a phase profile is mutually exclusive with actually getting the call path information. You can have either or, but you can't have both in any given instrumentation of your code. So if you do compile your code with to look at a phase, then you don't want to set the tau call path variable. That won't work at runtime. The phase, to get the phase, is actually, let's see if I show it here. No, I don't. You actually have to use a makefile, a tau makefile. So has nothing to do with your makefile, but you need to use one of the pre-configured tau makefiles, or you have to set the tau makefile and variable to point to one of those tau makefiles that has phase in the title. So you saw before, there's various designations here, right, for PAPI, MPI, PET, PGI. So so one that will enable phase profiling should have a dash phase somewhere in this title. So you point the tau make, this environment variable to one of those tau make files that has that in it and that has the other combination of options that you need. And then you just compile as normal and make sure that you don't try to get call path information during that run. And that will give you a phase. And so when you bring up tau, anything that happens in here will be labeled with this phase name that you give it, and you can separate it out from everything else. And again, I'll show you what that looks like. So that means that we can go from, so this was the situation before when we instrumented unres with tau. We can see the startup time totally dominates this short run, and we don't know what are the really important functions that we're interested in for the production part of the run. But since we can isolate the loop, the main loop, molecular dynamics loop in this code, we can isolate that with the phase profile. And so I define this as the phase MD, and so now this is what it looks like when we profile with tau. So we have a very clean profile of only those functions that are called during the main loop. And so we can now clearly see what is the most time-consuming function and the other functions that may be important. So we'll go through how to get some of these views momentarily. But we're just kind of moving through this story of this process of the performance engineering. So we've taken a look at the overall serial and parallel performance of our code. We've looked at where the code spends the most time. We've tried to instrument and isolate those functions that are most important to eliminate overhead and also to make sure we're measuring the region that we're really interested in. And so now we can, if we want to look at the serial performance, we can now take a look at using hardware counters to get more information about how the code is performing. Given, in those specific areas that we're interested in, not just overall, but in specific regions of the code, a given function or even a given line of the code, we could if we wanted. Okay. So we talked already about hardware counters. These are can be used to help us to figure out if we're not getting, for example, the floating point efficiency that we want. We can try to figure out why that is. Are we running into cache problems where we're trying to access we're accessing variables that are not found in the cache, so we get a cache miss, and that takes many cycles to get that variable that we need into the cache and into the register so that we can work with it. So we can measure different events on the hardware. We can look at if we're having a hard time getting memory or getting the variables to the processor in a timely fashion, then the floating point registers may sit idle, and so you can look at all these things, and you can look at that in very fine detail. So we already talked a little bit about using PAPI to do that. I mentioned these two commands, PAPI avail to look at the standard PAPI counters, and PAPI native avail to look at the actual hardware-specific counters for a particular architecture. So you can run this. So you want to run these commands on the compute node that you're actually going to be running the code on. The login nodes may or may not give you an error, depending on if they're configured. I think on Kraken they probably would, for example, since the PAPI, this command is going to be configured to run on the compute nodes, which run a different operating system. So anyway, you want to make sure that you get that information from the compute node. So you find out which counters you're interested in measuring. You run tau. Maybe you define a phase so that you can isolate region of interest. So the way that you specify this is just like you tell it that you want to get call path information. You just set an environment variable, and the environment variable is tau underscore metrics. And then you give it a list of however many of the specific PAPI counters, or there's some general ones too, and these are listed in the tau documentation. All machines have this get time of day. I think a finer resolution time, this is just a general timer. I think there's one called Linux timers if you're running on a Linux machine, which is supposed to be a finer resolution clock. So you set those, and you separate those by colons. So we've got get time of day, and then we've got the floating point operations and the total cycles defined through the PAPI, the standard PAPI interface. So you'll need to know, and I believe I'll have to double check, but so PAPI avail and PAPI native avail give you some information about the architecture that you're running on. For example, I believe they do tell you how many counters are available, how many registers are available at a given time. So that will tell you how many different events you can monitor at a given time. And if you don't get that there, then you just have to look it up for the architecture that you're running on. And so then you could set as many counters as you have space. Some counters are mutually exclusive. There are some things that you can't measure simultaneously, even if you have enough registers to do it. And there are commands in PAPI avail. You can give a list of arguments to PAPI avail, and there may be a command line option there, I forget. But you can give it a list of arguments of the counters you'd like to run on a particular machine, that you'd like to check on a particular machine at a given time. And it will give you, it'll spit back an error if they're incompatible, or probably if you tried to specify too many, it would also tell you that. So you can double check before you run with PAPI avail if the counters that you think you can get and that you want to get, you can actually measure simultaneously. And if you can't, then you just have to do separate runs specifying those at different times, and then extrapolate from that the information you need. So this is just an example of, so after we build a code like unres, and we built it, we made sure to build it with a tau makefile that had PAPI in the title. So we've got PAPI support, and then we set this tau metrics variable. And so then in paraprof you can bring up a list of all the functions here in the code that you instrumented. And now instead of the time spent in each of those functions, you can see, so there's a couple of things you can do. You could just have it give you the straight floating point operations, or you can click on options. So that's the instructions here tell you. You could click on the options here, and it would say show derived metrics panel, and then you can actually create an expression where, say you want to get the floating point operations per cycle shown, then you can divide that right within tau and create a new metric for it to show. And so that's what we did here. So now it's actually showing the floating point operations per cycle, and that's kind of nice because, like I said, you can easily find out the theoretical peak floating point operations per cycle for a given architecture, and this can show you on a function by function basis how